Hello there. Isn't this nice? Now it's like we can talk to each other. Like I can almost look into your living room. Or are are you watching this in your bathroom? Come on now. Goodness sake. We're going to talk about collisions today. This is one of my favorite parts of this course. So, I'm going to give you an example. This is called a Newton's cradle. So, when you lift one ball and let it drop, you're giving it some momentum. It has mass, it's going to have velocity, and so when it collides with these other balls, it's going to transfer its momentum all the way to the other side, and this other ball coming out of here should have the same momentum as the original ball had. Okay, it's not going to work perfectly because I have to hold it up like this, but still. Here we go. Just watch this forever. So if it was built perfectly and it was completely stable, theoretically it should just keep going forever. Or if you took two balls instead of just the one, now you're increasing the incoming momentum by increasing the mass. And so these other three, if they'd ever stop bouncing, will act differently. Now the outgoing momentum has to match the incoming momentum. This is called the conservation of momentum. So we're going to show mathematically why it should work that way. So before a collision, you've got an incoming ball right here and an incoming ball over here. It actually doesn't matter if they're both moving or if one is standing still or whatnot. You have both balls coming in, they have velocity and mass, which means they both have momentum. During the collision, each ball is going to exert a force on the other ball. So ball number one is exerting a force on ball number two, right there. And according to Newton's third law, the other ball has to be exerting the same force on the first ball. Okay. Now, when you have a force exerted on a mass, we know that there's going to be an acceleration. And so that's why they change directions. So ball number one was moving this way at the beginning, but because of the force that was exerted on it by the other ball, it's now moving back where it came from. Now, here it is mathematically. We know that the force exerted on ball number two is the same as the force exerted on ball number one, just in opposite directions. That's what this part says right over here. Okay, and then we expand that force into its formula, mass times acceleration. That's step number two, right over there. Okay, now we also know that acceleration has its own formula, final minus initial velocity, divided by change in time. So that's where this part came from. This is the acceleration formula, just expanded into its pieces. Now the next thing that happens is that this mass is distributed into the brackets. Over there, same thing with this side, the mass is distributed into the brackets. And because we have a divided by time on both sides, that divided by time can get canceled out. Okay, so our next line now shows the distributed version of the formula. So mass 1 times velocity 1 final. Notice that is momentum. It's final momentum. Okay, and this one over here would be ball 1's initial momentum. This is ball 2's final momentum. This is ball 2's initial momentum. So what this is really saying is that the change in momentum over here is equal to the change in momentum over here on each side of the equation. We can add the negative ones to the opposite side just to make this a little bit cleaner. But when we do that, so we're talking about this line right over here, when we do that, we end up with ball 1's initial velocity times ball 1's mass to give us ball 1's momentum on this side, plus ball 2's initial momentum. So that's the total initial momentum equals ball 1's final momentum plus ball 2's final momentum. So that's all the initial momentum on one side on the left and all the final momentum on the right. And that's what this final piece over here says, that all of the initial momentum in ball 1 and ball 2 together is going to be equal to the final momentum of both balls together. It's going to have been redistributed somehow, but they're going to have the same momentum all together. So what does this mean? This gives us our formula for the conservation of momentum, which is P1 equals P2. Okay, this is a vector, this is a vector. So this is momentum at the beginning. P1 is total initial momentum. And P2 is total final momentum. So the total momentum at the beginning of the collision, before the collision happens, is going to be equal to the total momentum of all objects after the collision happens. Now, different objects collide with one another differently, and so we have three main types of collisions. We are going to assume that no momentum is lost because of friction or air resistance, so we're living in a perfect world right now. So the first type of collision is elastic collisions. So two objects collide and rebound. Think about pool balls. That's usually the best example. When you hit one pool ball off of another, they just bounce off of each other perfectly. They don't stick together. There's no squishing that happens like if you were to throw two sponge balls against each other or something like that. You just have one ball moving this way, the other ball moving this way. So this is at the beginning or before collision, and then after collision, they are just moving away from each other. So the objects collide, they bounce off and move back where they were coming from. Now that's just things moving straight back and forth like this, but things don't have to bounce off of each other straight back and forth. They could glance or something like that. That would also be considered an elastic collision, as long as they're not sticking together or something like that. So the sticking together version is the inelastic collision. Two objects collide, but then they lock together during the collision. Okay, so before the collision, let's go with, before the collision, let's say you have a truck. Perfect, this is my dream truck. It's traveling this way. You also have a tiny car, and it's traveling this way. So this is before collision. They both have some sort of momentum. Probably the big one has more momentum than the little one. And then after collision, we're saying that they get stuck together. So our big truck over here and there. Now they're one vehicle. They're probably moving this way. So the two objects collide and they become one object, essentially. Okay, so they had separate masses at the beginning, but now they have a combined mass at the end. And the final one is explosions. So we're going to start off with your classic cartoon bomb. Oh, we need proper sparks here. Okay, so this is before. Now this, like, you can't really call it a collision, right? It's an explosion. It's not two things colliding, but still. So after, you're going to have your one object becoming multiple objects. Okay, so before you had one single object, and after, you're going to have, oh, let's see if I can do this now. After, let's say you have three objects, and they're all moving off in different directions. Okay, so this is the third type of collision. It's an explosion, but you start it off with one object and it separates into many objects. So our first one, an elastic collision, you started off with more than one object. It doesn't have to be two, could be more than that. You started off with more than one object and ended up with more than one object. Inelastic, you started out with two objects or more and they become one, and the explosions one, you started off with one object and it becomes multiple. Okay, but again, it's a gray area. Usually collisions don't perfectly fit into any of those. So if you think about a car accident, one car T-boning another, they don't bounce off of each other perfectly like pool balls would. They also probably don't just stick together like the little car and truck that we have over there. They kind of do both. They do a little bit of bouncing off of each other, but they also do a little bit of absorbing of the impact because they squish together. Let's do our examples. A basketball with a mass of 0.7 kilograms and a velocity of 2 meters per second, and a soccer ball with a mass of 0.45 kilograms and a velocity of 0.2 meters per second are rolling toward each other on the gym floor. Very exciting. The two collide and rebound in the directions they came from. If the basketball rebounds with a velocity of 1.5 meters per second, what is the velocity of the soccer ball after the collision? So you have two balls traveling toward each other. There's the basketball moving this way. Here's the soccer ball moving this way. And they're going to collide, rebound off of each other. And it says that the basketball rebounds with a velocity of 1.5 meters per second in the direction it came from. Okay, so at the end, let's just call this basketball, soccer ball. So in the end, you get the basketball rebounding the way it came from, and the soccer ball also rebounds in the direction it came from, but we don't know how fast. So that's what we're trying to calculate here. So we're going to use the conservation of momentum, P1 equals P2. P2. And then we're just going to split the P into all the momentums that were occurring at the beginning and at the end. So at the beginning, we've got the mass of the basketball, mb, times the velocity of the basketball at the beginning, mbvb1. This is going to have a lot of subscripts, so bear with me. And love it. It'll just make your life better. Plus, we actually want minus. Here, let me fix this. Well, let's go plus MSVS1 equals MBVB2 plus MBV MSVS two. There we go. Now I've fixed it. Okay, all of these things are vectors, and so although I haven't put the directions in front of the momentum terms, I'm going to put the directions in the velocity. Okay, so let's say that this direction is positive, this direction is negative. Okay, so according to our diagram over here, the basketball's initial velocity is positive and its final velocity is negative. Okay, so now we're just going to put in our numbers here and solve for the missing piece. So the mass of the basketball is 0.7 kilograms. The velocity of the basketball at the beginning is 2 meters per second. And that's going to be positive because that's what we named that one. Plus 0.45 kilograms times the velocity of the soccer ball at the beginning, which is going to be negative 0.2 meters per second. Okay, it's the opposite direction, so it should be negative. And that's equal to the mass of the basketball, 0.7 kilograms again, times the final velocity, which is going to be negative 1.5 meters per second because it rebounded the way it came. And the second part is the mass of the soccer ball, 0.45 kilograms, times its final velocity. And that's the one thing that we're trying to solve for. Okay, so we have everything filled in this equation except for that last piece, the velocity of the soccer ball. So at this point, it's just an algebraic equation. We're just going to put everything together and then solve for VS2. So we're going to put, first of all, this side together. Then we're going to subtract 0.7 kilograms, or add it, I guess, because it's going to be negative, and then divide by 0.45. Okay, our final answer is going to end up VS2 equals 5.2 meters per second. And that's positive. Okay, this is a bit of an odd answer, I guess. So it's moving way faster than it was at the beginning, and it's moving faster than the basketball was either. So what's happening here to suddenly get a really fast-moving soccer ball? So the basketball is heavier, it has more mass than the soccer ball, and it loses some of its momentum, right? So at the beginning, it was going 2 meters per second, this one over here, and at the end, it's only going 1.5 meters per second. So it has lost some momentum, which means that the soccer ball has gained that momentum. Okay, so the soccer ball has gained 0.7 kilograms times 0.5 meters per second, that much momentum. Okay, and then when you translate that into the velocity that's added to a 0.45 kilogram object, it turns out that it's going much faster. Okay, so this is our final answer for velocity of the soccer ball at the end. And now example 2. A 1,050 kilogram car is moving 25 meters per second east and has a collision with a 3 times 10 to the 3, or 3,000 kilogram truck moving 20 meters per second west. The vehicles locked together in the collision. What is their velocity after the collision? Okay, so we're given the mass of the car and the mass of the truck. We're given the initial velocities of the car and truck, and we're just asked to find what's the velocity of both of them together after the collision. So we're going to use the same thing, conservation of momentum. Well, I guess we're doing it in green now. P1 equals P2. The momentum at the beginning equals the momentum at the end. So now we're going to look at what are all the momentums that existed at the beginning and what are all the momentums that existed at the end. So the momentums at the beginning were the car and the truck. So we're going to go the mass of the car times the velocity of the car at the beginning plus the mass of the truck plus times the velocity of the truck at the beginning is equal to the mass of the car truck, hey, why not, times the velocity of the car truck. I could say at the end, but there was no car truck at the beginning. Now that you mention it, I don't really need the ones over here either, because there weren't final momentums for the car and truck. So now we're just going to put in all our numbers. So 1,050 kilograms is the car. The velocity is 25 meters per second, plus the mass of the truck, which is 3,000 kilograms, times the velocity of the truck, which is 20 meters per second. But these are moving in opposite directions. So let's make this one negative, though it doesn't matter, you can do whatever you want. So now that I've named the 20 meters per second negative, that means that west is going to be the negative direction. So west is the negative direction, east is the positive direction. Again, it doesn't matter. You can do whatever you want, as long as you're consistent in your calculation. Now, the mass of the car truck is just both of them added up. So the car is 1,050, the truck is 3,000, so that's 4,050 kilograms. And then we're looking for what's the velocity of the car truck in the end. Arrows, 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 because all these are vectors. Okay, and again, solving for it now is just algebra. You can put together the left side and then divide by 4,050, and so you get a car truck velocity of 8.3 meters per second, but negative. Okay, and so our final velocity then, we should translate that negative into a direction. So the velocity of the car truck is 8.3 meters per second to the west. Okay, so this is going to be a common strategy that we're going to use. You start off with looking at conservation of momentum is what's happening, and then we look at what are all of the things that had momentum at the beginning, and we put them on the number 1 side, and what are all the things that have momentum at the end, and put them on the number 2 side. So that strategy is going to work for every kind of conservation of momentum question.